Hello folks, so in this video I actually want to talk about another way to see this formula, and this way that I'm going to show you might look a little simpler, and it actually might look familiar if you talked about compound interest when you were taking maybe Algebra 1 or maybe even Algebra 2. Ready? So this formula, when we look at it, there aren't too many pieces to it, although there are a number of variables or different parameters to it. But at the end of the day, it is really just an exponential function. In any given scenario, the principal amount doesn't change. You invested however much you invested. The interest rate of the account, again in most of these problems anyway, does not change. Savings accounts sometimes do change their interest rate, but we won't get too far into that. But for the purpose of these problems, they will stay the same. And likewise, the number of times a year, or how the frequency that the interest compounds or is paid out, doesn't change either. So really, the only thing that actually changes is time. And so really, you can write this a as a function of t. Okay. So let's go back here. Let's take a look at an example of this scenario, but not really using this big equation. Ready? So let's pretend you invest, I'll just say P is, say, $100 in this example. Let's suppose that your interest rate is, well, let's say 8%. Just made that up. And we're going to say that's also compounded. We're going to say monthly here. Okay. What I'm going to do is I'm just going to create a table of the amount of money in your account as time goes on. And the way I'm going to count this is by compounding periods. So I'm going to create a little table here. Right here. So this will be the number of compounding periods, and I'm just going to abbreviate that. In other words, so a compounding period is simply how long it takes for you to get paid the interest. So since we're being paid monthly, this is going to be essentially the number of months passed since you opened it. And over here we'll have the amount, which will be A. Give that in dollars up there. So let's say we start off, so month 0, we have $100 there. Nothing too crazy. In 1 month, so here's how this works. Since we are compounding monthly, the way this works is our annual interest rate of 8% is broken up into 8 over 12%. And we earn that much interest every month, and so at the end of the year, theoretically, you have gained actually 8%. So again, it's just another way of breaking that 8% down. Instead of 8% all at once, you're getting paid in installments, if you will. So we actually gain, or our interest is 8%, but actually only 1/12 of 8%. So I'm gonna write it like so. So how much percentage is that? Well, that actually comes out to 0.08 over 12, which is 0.006 repeating. Okay. Now, if I was actually to do this, a way to represent a percentage gain is actually to multiply it by 1 plus that decimal. And what I mean by that is I can say the actual amount in my account at this point is 100 times 1.006, repeating. Okay, so what this actually is, again, to actually see this, is let's say I gain, well, there's a little aside here. Let's pretend I start with $100, like we did, and let's just say I gain 8%. Well, you're going to be doing 100 plus 8% of 100, which is 8. So 100 plus 8. But another way to get this is to write it as 100 times 1.08. So that's how you that's how you write out a percentage gain by multiplying. Alrighty. If I was to actually calculate this, this will come out to $100.67 after rounding. Okay, so that's after 1 month. if I go to 2 months now, another month goes by, so now we gain again the same percentage, so that's going to be 8/12%, which is again 0.006. But remember, we're getting that of, because compound interest, of whatever we had previously, so of $100.67. Oops. How would I represent that? Well, I'm going to be writing it like this. I would start off with $100.67 times 1.006 repeating. Okay, I said that this is going to look just like an exponential function. So actually, instead of writing it like that, I'm going to substitute this expression right here. And so actually, after 2 months, I have this much. And again, it's the same amount, I'm just writing it differently, times 1.006 repeating times another one. That's really just 100 times 1.006 squared. Right. Now I think we can see that this is actually just an exponential function. And so if the number of compounding periods is whatever it is, I'm just going to call it x, then the amount I would have is just 100 times whatever that multiplier is to the x power. Okay, remember, x is really just the number of compounding periods. And I mentioned this in our other derivation of the compound interest formula. The number of compounding periods, again, is just, that's equal to the number of times it compounds per year, number of compounding periods per year, sorry about that, times the number of years. And so with a little bit of dimensional analysis, we have, this is n, and this is t, our years will cancel, and that will give you the number of compounding periods that have gone by. If we break this part down here, this is really just 1 plus 0.006, and again, where did that come from? That came from this. This part right here is r over n. And so that's where this formula comes from. So really, this formula is just a more generic version, I suppose. Generic might not be the right word, but it's another way of just writing out this formula right here. Okay. The thing you want to be careful of is, depending on how you're compounding, the x might not represent years. So for example, in this scenario, in blue here, x is given in months. The number of compounding periods is determined by the months because it's compounded monthly. This formula kind of doesn't care about it because, well, t is always given in years, and so the n times t kind of accounts for that already. Alrighty. So hope that video was somewhat interesting, and hopefully now we can see that this is really just a kind of fancy exponential function. Alrighty. Thanks for listening. I'll catch you in the next one, folks.